Hello, and welcome to the next episode in my Modern Java by Example webinar. Today, we're going to look at a really cool example, which is going to be an asynchronous version of the recursive directory creation and processing application we looked at yesterday, except rather than using sequential streams and parallel streams to do the processing synchronously, instead, we're now going to use the Java Completable Futures framework to do all the processing asynchronously. And this particular example I'm very proud of this particular example because it really shows off some amazingly powerful features that are part of Java Completable Futures. So let's go ahead and dig right into it. Once again, it looks like GitHub is up and running again, which is good since it was down yesterday. So let me go ahead and share my screen, and I'll remind you briefly where the code can be found. So if you go to my live lessons folder and my live lessons repository at my GitHub account, and you go to the folders folder and you click on async, that will take you to all the code we're about to look at today. So that's the location of everything. And then just a real quick recap of what we're doing. So if you take a look, if you go into the directory that's the resources directory for all this stuff, you'll see that there's a very large recursively structured folder hierarchy that contains all the source code and project files and so on for all the live lessons examples I've done over the years. And there's about 2,000 files and folders in here. So if you look at this, there's lots of stuff. And what this program is going to do is it's going to read in all that content, build an internal in-memory data structure entirely asynchronously, and then it's going to go ahead and do various processing operations on that recursively composed data structure, also entirely asynchronously. So there's lots and lots of asynchrony going on here. And it's really fun to kind of compare and contrast this approach with the synchronous approach we looked at yesterday that used sequential and parallel streams. A lot of the overall design is the same, but the processing logic is quite different, as we'll see in a minute. So let's go ahead and jump right in. Let's take a look at the main program. This is somewhat similar to what we looked at yesterday, but everything's asynchronous as opposed to synchronous. So as you'll see, we have our directory that we're going to use to store all the files we're going to traverse and the folders. We have a completable future that's completed to be null called sVoid. You'll see what we use that for later. It's a way to make everything work in a consistent way. Here's the main program. First, we're going to run all the asynchronous code in a synchronous manner. And I'm not going to focus on that at first. I'm going to focus on the asynchronous stuff, and then we'll come back and look at the synchronous stuff. And the reason that I did it synchronously was to make the timing accurate. And you'll see why we need that in just a second. We're then going to look at we're first going to look at the asynchronous test. So that's what we're going to look at. And all these things, as usual, are measured, and then we print the results. So just for kicks, let's go ahead and run the program so you can see what the results are going to look like. And you'll see why I run it both synchronously and asynchronously. So as you can see, we do a bunch of async operations where it's all asynchronous. And those execute in blazingly fast time, or so it appears. And then we also have synchronous versions of all this stuff, which use the asynchronous mechanisms, but they do a join at the end of each test. So it blocks until the test is done. And you'll notice that they appear to be slower. Well, really, of course, what's happening is that these operations we're doing asynchronously are simply starting everything up asynchronously and then returning a completable future. And then we have an operation called join, where we join everything that's running asynchronously. And you'll see that the asynchronous results join is where the bulk of the time goes. And that, of course, is because we're not counting the time spent starting everything running asynchronously in the tests. Instead, we're recording all that at the end when we join. And you'll get a better sense of that as we go through the example. But it's really kind of interesting, and it demonstrates I think quite conclusively the tricky parts of trying to do asynchronous measurement. So measuring performance asynchronously is a little bit tricky. All right, so let's go ahead down and now look at the async test code. So same operations we looked at yesterday. We're going to create a folder, except now we're going to do it asynchronously. We're going to take that folder. We'll get back a completable future to that folder. And then we're going to go ahead and run a bunch of other processing operations on that folder. That folder, of course, is created asynchronously. And once it's done, we're going to go ahead and count the number of entries in the folder. We're going to go ahead and search for a search word in that folder. That will also, of course, be asynchronous. And then we're also going to go ahead and count the number of lines. The counting of the number of lines runs in an asynchronous manner, but the actual counting is done synchronously. And you'll see more about that when we look at the individual pieces of code. Before I get into this too much more, though, I want to kind of talk about the overall structure of the test, because they're also rather clever too. So you can see here that we go ahead and time how long it takes to create the folder asynchronously, but we don't actually wait for it to be created. We just wait to kick everything off. And we get back from this a completable future. And I've gone back and forth on this. This is actually a case, I think, where I like to use the var keyword, because var allows me to get rid of this incredibly long, verbose, completable future to durant thing. I put it there as a comment just because I haven't quite convinced myself that var is the way to go, but I think it's more concise. Down here, this is actually also a var, and that's a completable future to a stream of voids. And we'll talk more about that in a second. Okay, so what do we do to run the tests? We use the stream of factory method, and we're going to go ahead and give it a bunch of asynchronous functions, which are going to run the tests asynchronously. And these are all rather cool. So you can see we have a couple different types. We have one called run function async, and there's two variants of that. And then we have another one called run by function async. So let's go ahead and take a look at those pieces of code because they're interesting. So here is run function async. Run function async takes a completable future to a durant, which may or may not be completed yet, right? We just started the whole thing asynchronously, and it may still be building that data structure in memory recursively and asynchronously. And when that folder is finally done being created asynchronously, we're then going to go ahead and we're going to apply the function that we passed in here. And the function we pass in is going to take a folder and return a completable future to void. And you'll see why we do the completable future to void thing shortly. And you'll see also that the return value of run function async is completable future to void. And we do that so we can start all of these tests running asynchronously and then wait for them all to finish in a common place. And you'll see what that looks like in a second. What we're going to do here is we're going to go ahead and run the function. And this particular function is going to either count the number of lines or count the number of entries. That's what gets passed in up here as the function. So these are basically very similar to the functions we looked at yesterday with only small changes. So that's what it's going to do. It's going to run that function in the background. And the way we're going to do it is by using a method called ThenComposeAsync. And ThenComposeAsync is a really cool completable future completion stage method that takes a completable future and an action. It takes a completable future to a previous stage, the one that was used to create the folder. And when that future completes, we then go ahead and rerun this operation here. And then ThenComposeAsync will run that operation in another thread in the fork join pool, in the common fork join pool. And what it does is we actually end up getting back here a completable future, and then ThenComposeAsync works as flatmap does for a stream or an optional or an RxJava observable, and it's going to go ahead and flatten it out. So we're going to end up with a completable future to void as the result. So this operation may actually go off and run in the background, but it'll return right away, and then we're going to be able to wait for it along with all the other operations that we do. So you can see we use the run function async here for counting entries and counting lines. We also have run by function async. So let's take a look at that. Run by function async is similar to run function async, except it takes a by function, not a function. And a by function, as the name suggests, takes two parameters. Basically takes, in this case, the string, the function that we're searching, they're going to do, and then a string to search for. So you'll see that we're going to be applying this function to a folder. So let's take a look and see how this works. So the by function takes a folder, and it takes a string, and it returns a completable future to void. So let's go ahead and take a look at this little driver code. This will call the ThenComposeAsync completion stage method when the folder has finished being constructed asynchronously. So all these things are going to be taking place at the same time. in different threads in the common fork join pool. And then we're going to go ahead and apply the by function, which is going to search for the word, the search word in the root folder. So that's basically what's going on there. So if we step back up here, you can see we pass in search folders. So what happens is the of method on stream will end up returning a stream of completable futures to voids. And it basically kicks everything off simultaneously. So this thing is going to start running asynchronously. We're then going to pass the root folder future into each of these helper functions, run function async and run by function async. They will return completable futures to void. We package those up into a stream of completable futures to void, and then we go ahead and we collect everything into a future collector, actually a stream of futures collector, and that will then return a single completable future, which when all the other asynchronous operations are done, it will go ahead and trigger. And what we do then is we go ahead and we join with that result. And so all this is doing is it's just using the completable future join method to wait for everything else to finish. The only reason I had to use join here was I didn't want my main program to fall off the end and shut everything down. If this was a server program, I probably wouldn't need to use join at all. I would just let it run until it was done. And in this case, I just did it because it's a client, and I didn't want my client to fall off the end of main before it finished. I could also put a sleep there too, but that's a little bit wonky. Okay, so armed with that information, let's now go ahead and take a look at the various methods that we're running asynchronously. Let's start first with create folder. So if you recall yesterday's tutorial, create folder was used to take an initial root path to a recursive directory structure and go ahead and synchronously create an object in memory called a durant or a folder that contained all the contents of the recursive directory structure, preserving that structure. So the root folder would contain a list of subfolders and documents. The list of subfolders would themselves contain other subfolders and documents recursively. So it's a nice composite data structure that we can then process in various ways. And yesterday's example looked at this using sequential streams and parallel streams. So all the calls that we saw yesterday were all synchronous, but when we ran it in parallel streams, we ended up having the different sources of the data run in parallel. And we'll come back and talk more about that because we had some good questions yesterday about how that all worked with respect to the batch splitterator. And I want to talk more about that, the batch folder splitterator, because that's an interesting thing. But we'll come back to that at the end. So here's create folder. You can see it uses folder from directory, except now, this time the folder, I probably should call it async folder because it's not the same folder as yesterday's folder. Now what this is going to do is it's going to do everything asynchronously. So this folder is actually going to have a from directory call that returns a completable future to a durant as opposed to just returning a durant. Let's go ahead and take a look at this. Here is the call we make, and it just goes ahead and forwards to this from directory call. And this is where things start to get really, really interesting. So the first thing I'm going to do is I'm going to make myself a little exception adapter because I hate checked exceptions with a passion. They make the code ugly and make it hard to work with functional programming and streams in a clean way. So I'm going to make something called getStream. This is pretty much like what we had yesterday. This is going to take a path, namely the root path, and then it's going to return a stream of the contents of that folder at that level. So if we start with the root, then it's going to walk through just the root folder and give us back the subfolders and documents that are in that one level. So we just limit this to one at a time. That's exactly like we did yesterday. Here's where things get different. What we did yesterday is we used this with either a sequential or parallel stream to do all the processing in a synchronous way. What we do now is we go ahead and we take our stream and we're going to go ahead and apply this particular walk function starting at the root, except we're going to do this in the context of a supplier lambda that will be arranged to be run in a thread in the common fork join pool. And the way we arrange to run this in the thread in the common fork join pool is by using the completable future supply async factory method. So supply async is a factory method that arranges to run the action, in this case a supplier lambda, in the fork join pool. And so what we're going to do, this is very similar to what we did yesterday, except now it's running asynchronously in the background. We're going to walk through that one level, filter out the root path to avoid infinite recursion, and then we're going to call collect to collect everything into the a completable future that will complete when everything else finishes. So unlike yesterday where we were collecting this basically into a list, now we're collecting it into a completable future to a bunch of stuff that will be off and running in the background. And as you'll see in a second, the toFolder call here uses an asynchronous folder collector, whereas yesterday we used a synchronous folder collector. We'll look at that in a second because that's kind of where the magic happens recursively. But I want to just kind of finish this off. What we're going to get back from this will be a completable future to a completable future. And you'll see why we get two levels of completable future here in a second. So to avoid nested completable futures, which are possible but ugly, we're going to use the fabulous ThenCompose completion stage method. And ThenCompose is very cool because it basically denests things. Again, it works like flat map on a stream. It works like flat map on an optional. It works like flat map on an observable, and so on. And what it's going to do is it's going to be called, it'll be called back after we get the completable future to the completable future. So we have a folder future here. When this thing is done, we get a folder future, and we take the folder future, and then we apply it using the function identity method. And believe it or not, this is a very clever idiom that allows us to denest these nested completable futures so we don't have to call join. That's the whole purpose of doing this, to avoid calling join. Because whenever you call join, you end up artificially restricting the amount of available concurrency that's going on in the system. You don't take advantage of the underlying mechanisms that are so cool. So the point of this is to denest it. It's a very important idiom to understand when you write advanced completable future code. Let's go take a look at the future collector we have here. This is a little different from the one from yesterday, but it's along the same lines. So here's the toFolder factory method. It makes a folder collector. Here is folder collector, like yesterday, takes a stream of paths, which could either be directories or they could be documents, subfolders or documents. It creates a folder, and it returns a completable future to folder, whereas yesterday's folder collector just returned a folder because it was all synchronous. So here's the constructor. It stashes this path away. Here's the supplier factory method. This returns a supplier, which when called by the streams framework, will go ahead and make us a folder at that path. So that's what's called the mutable result container. It starts off by making a folder that's rooted to that path. Here's the accumulator. The accumulator is also very much like what we looked at yesterday. It uses an add entry method defined in the folder class itself. And we'll look at that in a second because it does some really cool things. So basically, we accumulate the next path by putting it in the folder that we created by the supplier factory method. Here's the combiner. This is called, if we were to use a parallel stream, which we're not. So this is just here for completeness. It's probably overkill to combine parallel streams with regular completable futures. It's too much parallelism for its own good, quite frankly. So we'll look at merge in a second. And then the last method, which is really interesting, is called the finisher. The finisher gets called after the mutable result container has basically accumulated every element in the stream, every path. And it's going to turn around and create a single completable future, which when complete will return a completed folder, a folder with all the pieces put together. But keep in mind, all the processing that this thing is doing is going to be running asynchronously. So let's take a look at how this works. This is really, really powerful. It took me a while to figure this out, by the way. So down here we have a couple things. I guess I should show you the contents of folder first. So let's go take a quick look at what a folder is in a bit more detail. So yesterday's folder was very straightforward. It contained a list of subfolders and a list of documents. Today's implementation is going to be a little different. It will have a list of subfolders and a list of documents down here, except those things are only going to be created at the very end after everything is done running asynchronously. And up to that point, it's going to have a list of completable futures to subfolders and a list of completable futures to documents, which are in the process of being loaded asynchronously in threads in the common fork join pool. So that's what it's got under the hood. It's got these basically lists of completable futures. And that's very important to remember. When the folder constructor is called, it makes new lists of completable futures as well as lists of the folders, and they get filled in at different points. So popping back over to folder collector for a second, when finisher is called, we're going to go ahead and concatenate a bunch of things together. But before I show you that, let's go ahead and take a look at add entry first. So here's add entry. Add entry is what's called every time we get another element that needs to be added to our folder. And notice what's going to be added here is not a document or a folder. It's a completable future to a document or a folder, which is in the process of being downloaded asynchronously in the background. So this is where your mind starts to explode. So what we do here is we come in, we've got ourselves a path entry, and we check to see, is it a directory or is it a file? If it's a file, let's take a look at that one. That's pretty easy. What it does if it's a file is it goes ahead and it asynchronously loads the contents of that file. So here's how we asynchronously load the contents of a file. We go ahead and we make ourselves a little function called getBytes to work around the stupid checked exception stuff in Java. And then we go ahead and we asynchronously create a new document that applies this getBytes function, which will have the consequence of reading the contents of the file into a string. So this will all run in the background. So we're going to asynchronously open up and read the contents of the file. And if it's a big file, it could take a while to read. So that's why we do it asynchronously. And we get a completable future back from this. So popping back over here, this will give us a completable future to a document that's in the process of downloading. We stick that into the document futures list, and then we increment the size by 1 because we know that that will eventually finish. Okay, let's go look at the directory entries. They're a little bit more interesting. So directory entries, when we go ahead and add an entry that's a subdirectory, we're going to go ahead and use the from directory method. That's the one we were just looking at. So you can see the recursion that's going on here. And what this will do is from directory, we'll take the entry, and that will start to synchronously, sorry, actually I should say asynchronously and recursively create a future to a folder from the entry. So this is also working asynchronously. And now we do something very clever here. We use the when complete completion stage method. And when complete is a really interesting completion stage method in completable futures. It took me a while to really appreciate how cool it was until I started doing more advanced programs with it, like this one. And what when complete does is it always gets called, irrespective of whether there's an exception or a regular normal finish. So what we do here is if we get an exception, which is this parameter that I just used as underscore, 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 we're just going to ignore it. We're just going to let that get handled in the normal exception way. If it's not an exception, we've got ourselves a folder that is now finished being completed. And so what we do is we go ahead and we add the size here to this folder to the folder that we're creating. So we have created a folder and we're going to add that to the, we're going to basically have this subfolder. I guess I should probably call this thing a subfolder. That makes it more sense. And so this subfolder will then be added here. So you can see that we're going to add the size of the number of elements in the subfolder to the folder that we're in the process of creating. So this is cool because this will always get called when we complete normally, and it allows us to update the size at the right time after everything has completed. And I should probably also call this thing, like subfolder F, because it really is a subfolder. So all this computation is going to go on in the background, we're going to get back a completable future to it right away, and we're going to go ahead and plop that completable future in our list of subfolder completable futures. So after this thing runs for a while, we will end up with a list of all the subfolder futures and a list of all the document futures. And then if we pop back over to folder collector, we can see what finisher does. Before I do that, let me just show you merge. Even though merge doesn't actually get used in this example, just for completeness, let me show you what it does. When we merge two folders together, we can see that we go ahead and take the right-hand side's subfolder futures and the right-hand side document futures, and we add them to this subfolder futures and this document futures. We update the sizes, and then we just return this. And it's perfectly okay to return this. Not going to have to worry about race conditions or anything like that. In fact, you'll also notice that I think there are no locks whatsoever in this code at all. There's no synchronization required at all because of the magic way that the completable future takes care of all that for us on our behalf. Okay, so what we're going to do now here is go to the finisher. Now, when the finisher gets called, we reached a point where everything else has been completed. So we now have a list of subfolder futures that's comprehensive and a list of document futures that are comprehensive. And then we're going to go ahead and concatenate those two lists together using this little helper method called concat, which does some very clever tricks to work on generic arrays, which is pretty cool. So we're going to concatenate those two things together. So we're going to end up with an array of these elements concatenated together. So we take the two lists and we concatenate them together to make an array of completable futures to Durance. We're then going to check to see if that's null. If it's null, it meant we had a folder that had a subfolder that had no subfolders or documents. It was just empty. And then we just go ahead and return a completed future. Otherwise, what we're going to do here is we're going to take that array of both the subfolder futures and the document futures, and we're going to use the arbitrary arity all of method. Arbitrary arity all of is a special method that's part of the completable future interface that takes an array of completable futures, and it does not block. It returns a single completable future that will be triggered when everything that's running in the array of completable futures has finished. So what we're doing here is we basically have kicked all of this stuff off in the background running asynchronously, and then we end up with a single completable future. And when that single completable future completes, it's because all the other things that it was doing, like opening documents and getting their contents and building subfolders, all the asynchronous processing is done. And so when that completable future completes, the then apply method is called, and we call the folder when complete method. And folder when complete is just a little helper method I wrote that takes the list of completable future subfolders and the list of completable futures to documents, and it turns them into lists. And then we go ahead and store those in the subfolders and documents lists. So let's go ahead and take a look at collect to list. Collect to list takes a list of completable futures to Durance. And I could also go ahead and make this generic. I could make this type T, really. And it goes ahead and converts those into a stream, the completable futures into a stream, joins them all. So we end up then collecting that into a list of Durance. This is a very clever little trick that you can use if you need to do something like this. So it's a way of turning completable futures that are completed into basically a list of the objects that they were completable futures to, if that makes any sense. So very, very common trick. I should probably make this like a generic helper method and put it in my utils directory because it turns out to be reusable and very useful. Okay, so that's what happens here with the final thing that we're doing. Go back over here. What we get back from finisher basically is a completable future to a folder, and that completable future will finish when everything else is done. And what you'll get back essentially is going to be the folder when everything is finished. So it takes a while to get your head around what's happening here, because it's all occurring asynchronously. But that's really the beauty of the Completable Futures framework. It hides all those details from you. Okay, let's pop back over to the main program now. So that's what create folder did. Create folder went ahead and all the stuff I just showed you, all that mechanism is just used to get a completable future to a folder, which when it's finished initializing will have its completable future complete. Wow, that's a lot of stuff to think about. So if we go back up to the test driver program, you can see here that we started out by getting a completable future to that folder, and then we passed it into all these other methods. And so these other methods will then end up calling these functions or by functions, and let's go take a look and see what they do. So let's take a look at a simple one, count entries. Count entries is only going to be called back when the completable future to the folder has finished being initialized. And in that case, we just go ahead and create a stream of elements in the folder and count them. And you'll notice here, I decided to not get too cute. I just used a sequential stream. I could have used the same technique I used yesterday and used a parallel stream here to do that computation in parallel. I figured it probably wasn't worth it doing the counting asynchronously, but this works quite well. So this actually ends up using the breadth first search folder spliterator, which is a variant of the breadth first search folder spliterator we looked at yesterday. The main difference between the one we looked at yesterday, which was also a parallel spliterator, is that this particular spliterator is not a parallel spliterator. So if you take a look at this, it's just sort of a kind of a simplified version of what we saw yesterday. It goes ahead and makes a breadth first search iterator, which is, of course, a reverse breadth first search, as we talked about. Everything is done in try advanced because we're not implementing parallel stream version of this at all. And so what it basically does is it goes ahead and incrementally builds a breadth first search iteration of the folder structure and then works in reverse order. And the code here is pretty much identical to what we had yesterday. So the has next method will go ahead and see if we've got a null entry. If we do, and there's any folders, we remove the rightmost folder and then make that the current entry. And then we dump all of its subfolders and documents into the folder list and the documents list for this spliterator. Otherwise, if there were no folders, but there were documents, we go ahead and remove the rightmost element from that list, make that the current entry, and then the next method just gives back the current entry and sets current entry to null. So this logic is pretty much the same as we looked at yesterday. If we have a few minutes at the end, I'll come back and we'll look at yesterday's breadth first search iterator, because I want to explain why it worked correctly even when used with parallel streams. So I guess if I was really trying to be optimal here, I could use the same technique of conditionally turning the stream into a parallel stream, and it would run even faster. But I was really trying to focus on the completable future mechanisms here, not so much the parallel streams mechanisms. Let's take a quick look at the count lines method. This is another function. It takes a root folder, and it does essentially what we had done yesterday. It goes ahead and creates a stream from the folder using the breadth first search spliterator we just looked at. The folder spliterator only considers documents, and then it goes ahead and takes each document, splits the document up into a stream of essentially lines that are separated by new lines. And then for each document, it counts the number of new lines in the document, and then we sum all the results. Again, there are better ways to do this. This is just a way to show off some fun stream stuff. What I want to focus on, however, is this method. This is the one that does the searching. So if you recall, search folders that we looked at yesterday did the searching using parallel streams. Today, we're going to do the searching using completable futures. And here's what we're going to do. We're going to take the contents of the root folder, and we're going to go ahead and turn it into a stream, only consider documents by filtering out non-documents. And then for each document, we're going to go ahead and use the supply async method on completable future to check for the occurrences of the search word in that document. And we're going to do this all concurrently. And the way we do it is we basically have a stream of completable futures that are searching for essentially for the matches. And each of those different searches is going to run in a different thread in the common fork join pool, or they'll be queued up to run in threads in the common fork join pool. And then what we do is we go ahead and collect all these completable futures into a single completable future to a stream of longs, because we're using the stream of futures collector. And then once that one completable future is finished, then we go ahead and compute the sum by converting the stream into using map to long. So basically we're going to have a stream of long objects, reference types that we convert to long primitive types, and then we go ahead and sum all those things up. So this will also be running asynchronously for most of its processing, because it'll run the searches asynchronously, and each search just does this occurrence count, which is the same thing we had yesterday. Okay, so that's basically what I kind of wanted to show from an asynchronous point of view. I think you'll agree there's some really cool and interesting stuff going on here. The last thing I wanted to do was show you the synchronous version of all this stuff. And I did this in order to get the timing correct. So let's take a quick look at that. You'll notice that I had two batteries of tests. I had run sync tests and run async tests. And let's just rerun it quickly so you can kind of see the differences. And what you'll notice is all the ones that are the, quote, async versions all seem to execute really fast for the most part. Conversely, all the ones that are the synchronous versions, we're going to look at those in a second, all seem to take a lot longer time to run. Well, why is that? When we go look at the code, you'll see why that is. So let's take a look at the run sync tests method. So here's run sync test. What run sync test does is it uses this clever little hack where I make myself a one element array that's going to contain a completable future. And then I go ahead and I call create folders. Create folders, if you recall, runs asynchronously. I store the completable future in that came back from create folder. I store that in the one element array because I have to be able to pass this into a lambda. And then I join that call. So this entire thing here, including the join, that's the lambda expression that gets run in the time run method. If you go take a look at time run, you can see what time run does is it goes ahead and it takes that supplier, it starts the timing computation, calls supplier get, stops timing, and then it sticks that test result into the map under the name that we used there. So by this little simple sleight of hand, I'm able to time synchronous calls because I join on the completable future. So now I know exactly how long it took for that whole thing to run. And then I do the same trick for all the other tests. I do the same thing for count entries. I do the same thing for count lines. I do the same thing for search folders. I always pass in a supplier lambda that has the join call after I get the completable future back. And that way I can trivially go back and forth between testing the asynchronous performance with the synchronous performance. Now, really, the synchronous performance gives you a much more accurate view of how long these things take to run. The asynchronous stuff was just there to show how you could start all the tests running and then wait for them all to finish. And that's why if you take a look at the results, you get a much more accurate view with the sync versions that call join at the end. So searching the folders really takes, 67 milliseconds. Creating the folder really takes more like 263 milliseconds, give or take. Count lines takes 587 milliseconds. That's how long it really takes. But if you take a look up here at the async versions, they appear to take just about no time at all. And then all the time is actually being used by that one call to async results join, which is just waiting for all the asynchronous operations to finish. So hopefully that gives you a sense of what asynchrony is good for. It lets things finish right away, and then you can do the computations in the background. And only when you really need the results do you have to join to get them. And that's only for cases like this where we're just trying to have a client program that will block to not fall off the end of main. In a real production server or even a real production client with an event loop, you would probably run these computations in the background. Okay, so this is a good time to stop sharing my screen and go take some questions because it looks like there's a bunch of questions people have asked. Let's see, let's take a look at those. So one of the reasons to use completable future is to make sure the main thread does not block. Agreed. But if something is already running in fork join pool, what's the point of using ThenComposeAsync or some other async variant of the API? So keep in mind that the fork join pool has many threads. And so just because one thread happens to be running asynchronously in fork join pool doesn't mean there's not a whole boatload of other threads in the common fork join pool or some other fork join pool capable of running in parallel. So in this particular example, this computer I'm running with today has a quad-core, hyper-threaded processor. So it's got 8 effective cores. So there's basically 7 cores in the common fork join pool. And so in that particular case, I could always make my own fork join pool if I wanted one more thread. But basically what we're doing here is we're running things in the background, and then we use ThenComposeAsync to run that action in some other thread that's not currently busy in the background. So that's why we use ThenComposeAsync. I could have used another version of SupplyAsync, but I think that's ugly compared to using ThenComposeAsync, which is much more clean. There's also a ThenApplyAsync that does the same sort of thing. Can you elaborate what you said? It's not a server, it's a client. So that was what I talked about many times. This test program is a simple client. And it's a simple client, of course, because we want to make sure that the whole thing runs before the main function exits. So if I were to start this program and not put a join at the end, it would start everything running, and then it would exit. The main thread would go away. And because the threads that are in the common fork join pool are daemon threads by default, the whole program would shut down. So that would be a pretty pointless program, right? If it never did anything to show the results. So this is a very simple client where I want to block the main thread till everything else is done so I don't fall off main and get no results. If I was writing a server, on the other hand, I wouldn't need to do that. I would get computation in, it would do some work. Whenever it was done, it would give a result back. And that's because we would assume there'd be an event loop running the server, and when work came in, it would just go ahead and dispatch that work in threads running in the common fork join pool or whatever fork join pool we want to use. Likewise, in a modern GUI environment like Android, you would have a user interface thread, and that user interface thread would have its own event loop, and it would then run these computations in the background. And whenever those computations were done, they would somehow notify the user interface thread. And so that user interface thread would pick up the notification and display it to the user. But even in that case, if you were doing a GUI client and you weren't trying to run this in the main UI thread, you also wouldn't have to do a join. So you only have to do a join if you really want the result for some purpose, like not falling off the end of main. Can you give an example of reverse BFS iterator? So I think I just walked through it. So all this is saying is if you have a directory structure where you have a root folder, actually I'll tell you what, let me switch over here and I'll show you what is meant by reverse breadth first search. It's actually a very simple concept. There's nothing tricky about it. Let's go take a look here at here we go. So this is the directory hierarchy that we're traversing through. And as you can see here, we have works, which is the top level directory, and then works contains the live lessons subfolder and the POSA subfolder. And the POSA subfolder contains the EX subfolder, and the EX subfolder contains the M5 subfolder, and the M5 subfolder contains the simple image downloader subfolder. This will go on and on, but the point I'm trying to get to is finally we get down here where we've actually got, say, the simple image downloader app subfolder. And let's see, you can see there's lots of subfolders here. Let's just focus, let's see if we can find one that's fairly simple. Here we go. So you can take a look at this one. This is the simple image downloader subfolder, and in it, it's got 1, 2, 3, 4, 5, 6, 7, 8. I think it's got 9 documents there, starting at local properties and going to settings. And so all reverse breadth first search means is that when we built up the folder, the subfolder for this particular simple image downloader subfolder, it had a bunch of documents. And the documents would have shown up probably as local properties, simple image downloads, Gradle, Gradle, build.gradle, simple image downloader, IML, Gradle properties, Gradle bat, Gradle bat, and settings, Gradle. That would have been the order in which they were there. Reverse breadth first search just says I start at the end as opposed to the beginning of that list, and I go backwards. And I do that just to make it easy to remove the items and shrink the list efficiently. That's all it means. There's nothing particularly interesting or profound about that. And the same technique also applies for subfolders as well as for documents. We always start on the right-hand side and go it in reverse. Okay, let's see. Another question, we could have implemented searching functionality when individual documents are loaded. Well, that all, of course, assumes that at the time you loaded them, you knew what you were searching for. This particular program, I think I gave you some examples yesterday, but the concept of reading the contents of a recursive structure off of disk or off of out of memory or from a network or wherever you get it from, and then building a composite data structure, that concept is around, that's been used for things like abstract syntax trees and compilers. It's used for things like DOM trees and XML parsing, obviously building up our recursive composite folder structure. Once you've built that thing in memory, then you can do things with it because it's in memory. And so the idea here is we snarf everything up into this recursive composite structure, and then we can do searches on it rather than having to go out and search on disk. So it's basically just a way to bring it in. And I don't even want to get into the discussion about would there be ways of deferring the loading until runtime. Yes, of course, it's meant as an example to illustrate the point. It's not meant to be the exemplative way of doing large-scale recursive loading on demand of structures. That would be a whole other assignment. This is really to show off cool completable future techniques. Let's see. For timing calculations, could we also have used ThenApply sync API to populate the time in the map instead of using join? I'm not sure what ThenApply sync is. So you'll have to explain what ThenApply sync is. So help me understand what you mean by that. Again, so there's a follow-up question when the document is loaded. If you knew what you were searching for when you loaded the document, then of course you could have searched for it when you loaded it. The whole point here is that we build this data structure, and once it's in memory, we can do lots of searches on it. I just happened to do one search because I was just trying to show one thing. But in practice, once you build the data structure in memory, you can do all kinds of things to it. And the analogy, again, would be a DOM tree that you load into memory, and then you can do queries against the DOM tree. Similar thing would be an optimizing compiler that builds an internal abstract syntax tree, and then you can do operations on the internal syntax tree. So don't get caught up in the details of the fact we only search for one keyword after we built the data structure. Of course, we could have searched for every imaginable thing once we built the data structure. That was the point. Okay, what I want to do now is I want to go back over here and share my screen again. And let's take a look at yesterday's program real quick, because I want to show something interesting from yesterday's program that I didn't answer as thoroughly as I could have because I hadn't analyzed it at the time. So here was the question from yesterday. There's something called the batch folder spliterator, which is a superset of the BFS folder spliterator we just looked at. So this is from yesterday's example, and in that example we had basically sequential and parallel streams living together and being able to switch back and forth between them dynamically. And what I showed was that the batch folder spliterator contains, as part of its internal state, an iterator, and that iterator is initialized by the BFS iterator. And as you can see, there's just one instance of this thing. There's one instance of this, and then I have this thing called try-split. Now, try-split is a spliterator method that only is called when you're doing parallel streams. And with parallel streams, what you're doing is you're taking the data source and then you're splitting it up into chunks, and you're handing those chunks off to be run in parallel by threads in the common fork join pool, which is the way that parallel streams works. So the question that arose was, will you ever have a situation where multiple threads will be trying to iterate through this breadth first search iterator, because there are in fact multiple threads being processed in the stream in parallel? And I gave the right answer yesterday, but I didn't explain thoroughly why it didn't have any problems. So I put a comment in the code that explained it here, and I'll talk about this, and then we'll go look at the code and see what I'm talking about. So this particular iterator is only ever accessed in whatever thread is calling the spliterator, which let's say it's the main thread. It doesn't really matter what thread it is as long as it's only used by one thread. And therefore, since it's only ever used in one thread, this breadth first search iterator, BFS iterator, is only used in one thread, we don't have to worry about synchronizing it because there's never any contention from other threads. What's happening is that we're going to use this breadth first search iterator contents to create what we call a batch, which is an array that contains copies of the elements that we got through breadth first search. And every so often, when that batch array fills up, we're going to hand that off to the spliterator's spliterator factory method, which comes out of the box with Java. And that is going to then turn that into an array spliterator. And that array spliterator will then be handed off to another thread, which will then go ahead and use recursive decomposition to decompose that array spliterator contents to run in parallel, to break it up into little pieces. And the good news is that when it's converted into the array spliterator, that no longer impacts anything having to do with the breadth first search iterator, because it was just a copy of a subset of the breadth first search iterator's contents. And so that breadth first search iterator is only ever accessed in one thread. The fact that other threads are out there breaking up that array spliterator handed to it as a copy is completely unrelated to the breadth first search iterator, although it will, of course, help performance, as we saw, because the parallel streams version does, in fact, run faster. So if you take a look down here, you can see how this happens. We take a look in split batch, for example. What split batch does is it creates this new durant array, which has the batch in it. It copies contents from the iterator into the array, and then it goes ahead and turns that array over to spliterator's spliterator. And that's what will then go ahead under the hood and create an array spliterator. Take a look here. You can see it's making a new array spliterator from this. And the fact that that then runs in parallel is perfectly fine, because we don't have to worry about race conditions or any sharing of shared mutable state in our BFS iterator. And that's only ever accessed in one thread. So I wanted to kind of clarify that, because it's a little bit subtle, but the good news is this is a very common pattern. And if you take a look at the Java linked list source code from the Java collections framework, you'll see that it does pretty much the same trick as I'm showing here. It makes copies of elements in the linked list, turns them into an array, and then hands that off to the streams framework to continue processing it in parallel. Okay, so that's what I wanted to kind of cover from yesterday. Let me just give you a sense of what we'll do tomorrow. So if I get my act together and I can finish up my RX Java version of this family of programs, I will show you that. That may or may not happen. Not sure how many hours in the day there are. If we don't get that done, then there's a couple other really cool things that I can show you. There's some cool stuff that has to do with other ways of being able to process data structures like arrays using the common fork join pool and fork join mechanisms. So if you take a look here in my Java 8 folder, there's a really cool example that shows how to use fork join pools in some really interesting ways. And so we may look at that. That's EX22. And then there's also another cool example in here called EX8, which also shows off some really cool completable future mechanisms in a bit more kind of piecemeal fashion than a giant complex example like the one we looked at today. And there's other things we can look at as well. But what I want to do is try to finish off the week with the RX Java implementation of the composite directory creation and processing application. And that'll give us a chance to kind of compare and contrast the programming complexity. If I really get inspired, I may also take a shot at implementing some of these examples using the Reactor framework, which is, I think it's by Pivotal. From what I can tell, it looks a heck of a lot like RX Java, but supposedly it uses newer Java features like completable futures and Java 8, as opposed to what was done in RX Java, which was originally designed to work with earlier versions of Java, like I think Java 6, which lacked some of the cooler functional programming features. So they look very similar, so I want to kind of play around with that. The other thing I'm having a hard time getting my head around is the somewhat ridiculous names in the Reactor framework. Like instead of calling it an observable, they call it a flux. And I haven't quite figured out why it's a flux, but I'm sure I'll figure that out if I poke around there long enough. Okay, let's see. So thank you guys again, as always, for joining. If you have any more questions, feel free to send them to me by email, or feel free to post them on the Facebook page, or feel free to come back tomorrow and we will take them up and talk further. So thanks, you guys, and I'll look forward to talking to you later.